So here we are discussing one famous machine learning algorithm named K nearest neighbors. So there is a saying that you become the average of the 5 people you surround yourself with. So this is the main idea behind K nearest neighbors. What is KNN? It's a supervised learning algorithm. It's used for classification and regression. It makes predictions based on the closest data points. There is no training phase in this algorithm. You just tell me who your neighbors are and I will tell you what you are. So that's the basic idea behind KNN. So KNN classifies a point based on majority vote of its k nearest neighbors. So consider this label data set. So here these data points are labeled as class A, these are from class B, these are from class C. We got a new data point. Now let's say k is 5, right? So we are trying to find 5 nearest point of this new data point. We got 4 from class A and 1 from class C. So the new data point will be classified as class A. So what we are doing here? We are choosing a k or the number of neighbors. So 5 here. For the new point, we compute distance to all the points. We have to compute the distance of this new point to all the other dataset points. Then we'll pick the k nearest. Here we have picked 5 nearest and then we'll vote for the most common one. So in this case, this class A. What happens for KNN regression? So we choose k or the number of neighbors. For the new point, we'll compute distance to all points. But the data set we have, these are labeled but not with class, right? So we'll have some continuous values assigned to the data, let's say. So if k is 3, let's say we'll find 3 nearest data point and we'll take the average of these 3 and we'll assign it to the new data point. So this is the idea of KNN regression. Now how we'll calculate the distance? There are different distance metrics here like Euclidean distance, Manhattan distance, Minkowski distance, Hamming distance, Mahalanobis distance, right? So we'll discuss few here, right? Let's say Euclidean distance first. Let's say we have two data points A and B in 2 dimension. So A is x1, y1, B is x2, y2. These two data points. The Euclidean distance is this, right? So it will be square root of x1 minus x2 whole squared plus y1 minus y2 whole squared. For d-dimensional data, if A is x1 to xd, x1, x2 till xd and B is y1, y2 till yd. So the distance in d dimension will be the square root of the summation from I equals to y1 to d xi minus yi whole square. For Manhattan distance, so we calculate the x difference and the y difference in 2 dimension. So if A is x1, y1, B is x2, y2, so this distance will be the absolute value of x1 minus x2 plus absolute value of y1 minus y2. So the x difference and the y difference. So this blue one is the Manhattan distance. For d-dimensional data, also the distance will be summation of I equals to 1 to d, absolute value of xi minus yi. Next, Minkowski distance. So Minkowski distance for 2-dimensional data for A equals to x1, y1, B equals to x2, y2, it will be pth root of this whole thing. Absolute value of x1 minus x2 raised to the power p plus absolute value of y1 minus y2 raised to the power p. So this is the Minkowski distance. One interesting thing here is if p equals to 1, right, then we get Manhattan distance. If p equals to 2, we get the Euclidean distance. If p equals to tends to infinity, then we get this Chebyshev distance. For d-dimensional data, for a equals to a in d dimension from x1, x2 till xd, for b is y1, y2 till yd, the distance is pth root of this summation, the summation of I equals to 1 to d, absolute value of xi minus yi raised to the power p. So this is the Minkowski distance. Now cosine similarity and distance. So this is a different way of calculating distance. For d dimension, let's say if A is represented in this d dimensional vector and B is represented using this d dimensional vector y1, y2 till yd. So these two are the vectors and cos theta is the similarity between these two vectors, which is dot product of A and B divided by norm of A multiplied by norm of B. And the distance between these two vectors will get as 1 minus cos theta. So there are other distance metrics like having distance, Mahalanobis distance and all. So for different types of data sets, we can use different types of distance metrics. Next point is choosing the k. How we will choose the k? If k is small, our output will be overfitting the data and the output will be noisy. If k is large, there will be underfitting and smoother decision boundary. So we'll understand this with these examples here. So the first thing here is k equals to 1. If k equals to 1 here, there are two classes, let's say class A and class B or class blue and class orange, and this is the new point. K equals to 1, we will just calculate one nearest data point and we'll assign it to class blue. But we are not quite sure whether we should assign it to class blue or orange, right? If k equals to 5, we are calculating 5 nearest neighbors, right? So this 5 we got. And among this 5, we got 3 from orange, 2 from blue. So we'll assign this new point to orange data set. Here k equals to 5. What happens is k equals to 25, right? So it's like almost the whole data set, right? And for this new data point, we'll try to get 25 nearest data point, right? That means almost the whole data. And here we see 15 blue data points and 10 orange data points. So of course we'll assign this new point to class blue, right? But it's not the correct classification. We can simply look and say and this point should belong to orange class, right? So what happens when k is large? KNN doesn't focus on the local neighborhood anymore. Instead of asking who are my closest neighbors, it asks what does the majority of maybe the entire data set looks like. Next, often choose odd k to avoid ties in classification. So regression doesn't depend on odd or even k, but let's say if k is even for this example. If k is even, this is the new point and we have two classes, class A and class B, red class and this blue class. Then we can get just this two nearest point from class A, 2 point from class B. Then how do we decide whether to assign class A or class B for this new point? We can't, right? So there is tie, 2 votes for A, 2 votes for B, and KNN cannot decide the class without adding an extra tie-breaking rule, right? So which introduces bias and randomness. So if we have odd k, let's say k equals to 5, then we got 3 from class B, 2 from class A. We'll at least from one class we'll get some majority element. So will not have any tie. So chances of tie is most for binary classification, but odd k is always a safe choice for classification. The best method for choosing k is cross-validation. This is the most reliable approach. Is just to experiment with different k. What we do, we try different multiple values of k and evaluate performance using cross-validation. Choose the k that gives highest accuracy or lowest error. Now, there are few scenarios when we should not use KNN, like when the dataset is large. So, KNN must compute distances to every dataset point during prediction, right? So, it is very slow at prediction time and it's not suitable for real-time systems. The time complexity is order of n cross d, where n is the number of samples and d is the dimension of the data. So KNN is not useful when n is large, right? Next, high dimensional data having many features. In high dimensions, all points become similarly far. Distances lose meaning, accuracy drops dramatically. So, like one simple example we see here in 3 dimension, let's say this distance and this distance can be same, right? But this is from a different class, this is from a different class, right? So, distances are not helping doing KNN in higher dimensions. So, unless the dimensions are reduced by PCA or other dimensionality reduction techniques. Next point is when features are not scaled. So KNN relies on distance, right? So if one feature dominates, then distances become distorted and wrong neighbors will be selected. So without normalization, KNN becomes unreliable. Now, when the data is noisy or has many outliers, then also we should not use KNN. So with noise, what happens is small k means overfits, large k means underfits, and predictions will become unstable. Let's see this example here. So this is class A, the green ones. This is class B, the purple ones. And also we have some outliers here for class A here in this region. So this is the new data point we got. If k is equals to 5, we got this 5 data point nearest neighbors. Among these, 3 are from this class A, but these are outliers, right? 2 are only from this class B. But it looks like this point should belong to class B, but just because of this outliers, this point was misclassified as class A. So KNN is not useful on noisy datasets with outliers. When the data is imbalanced, then also we should not use KNN. So let's say this is one more example. Here we have 90% class A, this is the class A, and 10% only class B, let's say. Right? So neighbors always favor majority, right? So minority class rarely predicted correctly here. So if you see for this new data point, if you find this 5 nearest neighbors, 4 are coming from this majority class. Of course, there are 90% of this class A, right? 1 is only coming from this class B. So we'll classify it as class A. So most of the time we'll classify it as the majority class. So KNN performs poorly on imbalanced classification problem. When memory is limited, then also we should not use KNN because KNN stores the entire dataset. It's memory heavy, expensive for large datasets, and not ideal for edge devices, so not useful when RAM is restricted. So these are the scenarios, few we already have discussed, like when dataset is large, where high dimensional data is noisy, imbalance between classes, memory is limited, you need fast prediction. In these cases, we should not use KNN. Also, when we need explainability, and sometimes distance doesn't capture similarity. So there will be scenarios when distance will not capture similarity for some use cases. In those cases also, we should not use KNN. But there are few advantages also for KNN, like it's very simple and intuitive, no training time because we don't need to train the data. We just have the labeled data set and a new data points for which we want to predict, right? So it works well with small data sets and handles multi-class classifications easily.